So yeah, I'll be covering chapters 13 and 14, which first of which is functional language features, iterators, and closures. And this is a super useful chapter because tons of Rust code is written in a fairly functional way, and it's worth getting up to speed with writing in this kind of functional manner. I'm going to cover closures and how they work, processing things with iterators, using those skills to improve our IO project, and then also brief mention of the performance, though that was a tiny section, but still worth mentioning. You'll probably know closures by many other names as well as closures. So anonymous functions, functional literals, lambda function seems to be the winner in my mind, and then lambda expressions. They have their various nuances in different languages, but in closures we'll be talking about the Rust way. Go through what they are, the syntax, because that's kind of the key thing for writing any code with them, and how that behaves with things like capture lifetimes and closure traits as well. So they're unnamed functions, which you can assign to variables, and then you can pass them around as parameters. What makes them slightly different to just writing standard functions is that they can capture the state as needed around them. And Rust does this in a way that I haven't worked with before. The first thing to compare is functions to closures, because functions are obviously fairly familiar with. Here you've got a function that just adds 1 and returns a 1 larger number. In a closure form, you would indicate that parameter in between pipes, and then you would have your expression afterwards. You don't need the curly braces, you do need the pipes. You can also use the type annotations, just like a function, but again, those are optional. It will all just be inferred from the first use of it. A closure can also take no parameters, which is what that little example is at the bottom. But the calling code afterwards is identical. There's no way you'd really be able to tell the difference between calling a function and calling a closure. And as mentioned, those types that you can use type annotations for, they'll just be inferred from the first use of the closure. And then all subsequent uses have to be the same type. And that's because you've stamped out that particular struct with certain types, and it's only going to be that one. If you want it to be different types, you'll need to create a new closure. So what makes them different to functions and why people use them? Well, aside from convenience, is their ability to capture data. And Rust does this kind of implicitly. It doesn't tell you that it's capturing it. You can just use things in the function body, in your capture body, which I found quite interesting, because anyone coming from a C++ background, you immediately get, the warning signs of, oh, don't capture everything by reference, you're going to get in trouble. But don't capture everything by value, you're going to copy a load of things. So there's like a world of like, oh, dancing, being careful. But the wonderful thing about Rust is the borrow checker saves you from a lot of the errors that you would run into by capturing everything by reference. So in this example, you've got a mutable count outside. You then have a closure that references that count, and it's going to take it by reference, and then it's going to pass it into the print function, and then it's going to print the count using that closure when we call that closure later. The captured reference will live until the last lambda use, and that means that as well, usual reference rules are going to apply. So at any one time, you can have many immutable references, but you can only have one mutable reference. Whether or not that reference is mutable or immutable depends on what you do with it inside the function body. So in this example, because we've got an immutable reference to count in our print count lambda, and we're going to use that at the very bottom of this code block here, that means that we can't modify it, because then we'd have a mutable reference still live with an immutable reference also live. So if anyone's unclear about that, worth checking out the video back on lifetimes a few weeks ago. It's something that you can easily trip up on, but fortunately, again, the borrow checker just nags you until you get it right. So no drama. As I mentioned, that reference can also be taken mutably. So in this case, we've not actually written anything different other than that we are modifying the count inside here. And just by virtue of modifying it, you will be taking a mutable reference. And that means that you can't even take an immutable reference outside of it, because there can only be one mutable reference at a time. Once we've used it and we no longer have that mutable reference anymore, if we're done with using it, that's the last use, then you can do what you like with it again, just like the normal reference rules. You can also capture things by value. So in this example, a for loop captures its data by default by value. So I've got my vector of data, and because this is taken by value, that means that it's going to be moving the vector into it. So when I say taken by value, just to be clear, that is taking the reference to it, because a vector is a heap allocated type. So you can't, there's no copy constructor on the vector. So taking by value is moving it into it. So I'm moving it into this method implicitly. And because that's happening, I can't do anything with that data once I've used it. So here I've moved that into print vector. I then consume the data in my for loop, and I can call it once, but I can't do anything with it again. And I also can't call print vector again, because I can only access it once. So as mentioned, yeah, this means it can only be used once. It consumes the vector on the first call. And again, this is all done implicitly. It's not obvious, I would say. If you're completely new to Rust, you would think that if the earlier examples were fine, when you're modifying something inside it, then surely here it would also be fine. But the way a for loop works is it does actually consume this. If you didn't want to consume it, then you could pass it in by reference instead. So because my for loop is using it by reference, that means that my overall closure is also moving it in by reference. And that means I can use that vector as many times as I like. But there are cases where we actually want to move the data into the function. For example, if our action is going to happen on a different thread, then we want to make sure that our closure owns that data. So in this case, this would error because the current closure could outlive the current function that it's in, because I've spawned it off on a different thread. And that means that this data could go out of scope, and then this would be a dangling reference, but the borrow checker won't let you do that. So if you do need to move data into your closure, you can do that, and it's not going to happen explicitly. If it's not happening implicitly, then you can explicitly get it to move the data in with the move keyword. So here I'm just moving the data in. So even though this is by reference, I am actually moving the entire data structure inside. And that means, so this won't work. I can't use this here. I appreciate normally I've been commenting it out, but it's the same thing. So this would throw an error if you tried to execute it. It's worth mentioning as well that that move is a copy if it's on a copyable type. So things that are on the heap, you would have to do a clone. They're not copyable. But for things like an array of 1, 2, 3, even though I'm moving it in, a move of a stack type like this is just a copy. So you actually do still have access to the data. And that's true. The same with functions. It's exactly the same mentality. It's just remembering that idea. And that's, again, it's just because the data of a vector isn't stored on the stack. The thing you're copying is the thing on the stack. So if everything is on the stack, like in an array, then it's just a copy. It's fine. So what actually are closures? Well, as in many other languages, they're kind of just syntactic sugar for a special struct that's callable. And that struct can implement one of the following traits. We've looked at examples of all of these. So if your closure can only be executed once, so for example, if it's moving the data into it and that data is going to be consumed, then that means your closure can only be executed once and it implements fn once. If, however, it can be called more than one time, but its data is going to be modified, then that would be fn mutable. And then if it doesn't modify anything at all, then it can be fn. And the compiler is going to check those conditions for us. So yeah, so a closure that implements fn means it only takes immutable references to captured variables. Fn mute takes mutable references, and fn once might consume the captured variables. If something implements fn, then it trivially also implements fn once, since if it can be called once, it implements fn once. That's the only requirement on fn once. So that's the kind of order of precedence. So all closures that implement fn once because they could be called at least once. Closures that don't move captured variables also implement fn mutable. And closures that don't need mutable access even to captured variables also implement fn. So those are all our simple examples at the very start. Once we've got our closures, the main use case for it is passing them around as parameters. And you can specify what type of closure you want. So if you want to pass in a closure that you can call multiple times, then you can pass in fn mute. You can set your trait as fn mute rather than fn once, because if it's fn once, you can only call it once inside your function or anywhere. So this is the way that you pass in as a parameter. You'll notice that it's a generic type. And the reason it's a generic type is because, as I mentioned, it kind of gets stamped out like a struct. So it's actually a generic struct that you then declare the type of when it comes to actually get compiled. So in this example, we've said, okay, I want a closure and I want to return an I32, and I can specify that I want that closure itself to return an I32 and take an I32. So I can put additional strict kind of typing on the closure that my function is allowed to take, which is it's very clean. It's very easy to write that correctly, I found. We've actually used these closures in earlier chapters, and they kind of half mention it, but they don't necessarily go into as much detail. The classic example being when you've got an error. So unwrap or else needs to take a closure that knows what to do with the error. So you pass in, you say, okay, this function, this closure takes an error as a parameter, and then it's going to do this. It's going to print it, and then it's going to call exit. And those closures also make operating on collections much easier, which is why we then move on to the section on iterators. So in this example, we're saying, okay, I'm going to take my iterator, and then I'm going to call any. So then I can basically pull out anything where it's 2. Sorry, returns true if any of the items. So it says, are there any items that satisfy this predicate? Not doing a filter. And that any function on the iterator returns true if any of the items satisfy our predicate. You could have written arbitrarily complicated conditions in there. That's just a nice simple one. So the parameter is an item from the collection. It returns a bool, and the restrictions are that the closure must not consume its captures. And the way you know that is because it's got fn mute. So you couldn't pass in here an fn once. Sorry, you couldn't pass in something which doesn't implement fn mute. It can't mutate things in its closure. Sorry, it can't consume things in its closure because it's going to be called multiple times potentially. Which brings us on to the next section, which is going into a bit more detail about iterators themselves. Different types of iterators, and these are the main ones. So reft, you can take a mutable iterator, and then you can have an into iterator that iterates over the t values. You can also, so we've seen this on vector. You use it quite often. Anytime you're writing a for loop, you're implicitly using this. Anytime you're doing any of those iterator like .any, .filter, all of those things are implicitly using iterators. But we can also implement it ourselves. All we have to do is implement the next method on the iterator trait and associate what type of item we're going to be dealing with. And usually you would do this on a separate type, which would be your iterator type, just because it ends up being cleaner in the long run. Otherwise, it can get a bit messy. You can run into problems of things like modifying a collection, and it's not happy about you modifying a collection while you're editing it. So, for example, here, if we create an iterator struct, then we implement next on it, and we hold a collection in it, and we say, okay, it's also going to have an item associated type, which is this here. And we're going to carry around as well any state information. So in this case, I'm carrying a reference to my actual collection. And then my iterator implementation just involves the type, and then next, which is going to optionally return an item. And the reason it optionally returns an item is so that when you get to the end of the collection, you're not just going to keep going forever. So that way, the last one will be returning none. And then we're just going to increment the index and return something if we've got it from our collection itself. Once we've done that, we can use the iterator. So we can, for example, here, we're going to put a function on our collection to get the iterator itself. So we say function iterator. This is my new type that I just created here that implements iterator. And I'm going to say, when I call iter, I want you to return an iterator to the collection starting at 0. Once I've done that, I can then just on my collection. So if I create an instance of my collection, for example, then when I call .iter, I can then just do a for loop over it. I also have access to all of those nice things like .any, .filter, everything that you can do with an iterator, you can do with your custom iterator as well, which is really nice. You can also avoid having to call iter explicitly yourself either. So you might have noticed when you do a for loop on a vector, you don't have to do .iter. And the reason you don't have to do that is because you can implement into iter, which you can implement quite simply on your collection by saying implement into iter on this, turn the type. This is the type of the iterator, and then this is going to return the self.iter method. And that way it will implicitly just work for you. So I'm saying for item in graph collection, print the items. And as mentioned, you can then use all your standard iterator methods. So in this example, we're taking my collection, which is a custom collection, creating a new one, which I've set up to put some arbitrary items in it, saying iterate over it, and then I want to zip it with another new one, but I want to skip one each time. And then I also want to map some things together, and I want to filter it, and then I want to sum the result. And all of those things I haven't had to implement, but just by virtue of having an iterator implemented on it, you get access to all of that. So yeah, as mentioned, it's because these are all implemented on iterator. The ones that return iterators, so zip, map, and filter all return iterators. They are called iterator adapters, and they actually don't do anything until you try and figure out the results. So by either doing collect to get your collection of results out, or by doing sum to, for example, sum the results. So here's the example. This one isn't actually doing anything, whereas this one, because I'm doing collect, does actually do something. Nothing wrong with not doing anything, but you probably intended to, so it's worth knowing. Once we've got those tools under our belt, we can then use them to improve some of the code from last week's section. So in this example, it's cloning, it was cloning the arguments, but by switching to using iterators, you can then call args.next, which is doing almost the equivalent thing. But now we're not having to clone anything, we can just loop over it. In this example as well, so this was the before code, which is fine. These kind of for loops, if this, do this. But usually in Rust, once you get used to it, it's a lot clearer to write it in this more functional way. So I'm saying, okay, take the contents, get the lines, filter it by the query, and then collect them. So it's a lot more obvious, I would say, what's happening there compared to here, where you do have to reason about it because there could be things not quite how you expect, whereas there it's kind of some steps, and that's quite a Rust way of writing these operations. So that's quite a whistle-stop tour of chapter 13, but hopefully that's all right. So closures and iterators are very Rust, so they use them to express your intent. They make things clearer. Generally, I would say for loops are considered a bit passé in the Rust community. People don't use them as much anymore. It's much better to use iterators. You get a lot more for free with it, and you can do a lot more, and you can write some very clear code if you bother with iterators. With captures, initially you might find it strange that you get all these implicit captures, but by virtue of the way it's implemented, there's actually no downside to it figuring it out for you what you wanted to pass in because of borrow checker, which is nice. You're never going to get an accidental clone because, unlike in something like C++, when Rust says copy, it doesn't mean clone. It never means clone. It's never changing something on the heap, which means you're never getting an accidental heap allocation that you weren't expecting. And the implementation of closures and iterators are such that runtime performance should not be affected. It's the benefit of the ideal of zero cost abstractions. They gave some kind of values in there in the chapter if anyone's interested. I'm happy to take their word for it. I very much doubt it's the limiting factor in most of my code would be if there is any small overhead, but they say there isn't, so I believe them. That was kind of everything on chapter 13. Does anyone have anything they want to add on it before I move on to chapter 14, which is quite different? It's cargo and crates.
So you did mention about the chaining of the iterators and then that producing the lazy result that is not evaluated until collected, for instance. I think there might be a use case where you don't want to do it and potentially you want to return, but then it would be like a dynamic view over your collection, potentially from different if-else statements or something like that, right? And then eventually someone else calling that function would be collecting on it.
Yes.
But it is, I mean, for someone starting, it is kind of complicated. I tried that and it was complicated for me. So
yeah,
but it might be one of the use cases, right?
Yeah, definitely. You know, if you want to return an iterator, you can still evaluate that iterator later. It's still a totally valid iterator, even if it hasn't done the filtering yet.
It's very similar also to the views from the C++.
Yeah, definitely.
Yeah. Also, that chaining kind of so if you have for loops, if else statements and so on, it's like you're splitting your business logic with programming logic, right? Whereas like when you're chaining things, they are just making it clearer to express what your intent of the things is. And then it's also harder to screw things up because like if you have for if else's and whatnot, then like it's easy for another program just to add a line to do something in your loop, but that might not necessarily be what the whole logic is doing. So like I'm also finding it useful in other programming languages. All of them converge to that kind of way of doing things, right? So Python for a long time has it. Java since Java 8, for instance, has streams, which do basically the same thing. I think they have more performance penalty, runtime performance. With iterators, right? I think there is a compile time penalty a bit because it needs to create types around other types. And like if you get the error, sometimes it's really hard to read because if you map over your iterator, really what it does, it wraps with map type over another type that the original iterator was. And then if you have like lots of these chains, you eventually end up with so if there is a compiler error, it will tell you like a map of filter of something else doesn't match, but it is just a type, right? So yeah, it's just sometimes hard to read.
Yeah, definitely. Those kind of nested iterator types are, you know, the reason why people have such a problem with iterators sometimes. It's the reason why it's kind of hidden away quite a lot with modern IDEs and stuff. You just don't have to write out the iterators anymore, which is nice.
Yeah.
Okay, cool. So I will move on now to talking about cargo and crate.io. We've touched on this in various capacities in the past. This is going into a little bit more detail. You get a little bit more stuff to play with. It's quite a nice chapter. We're going to go through customizing builds with release profiles, how to publish a crate, which is super straightforward. Cargo workspaces, which we have talked about before, but we get to revisit them, which I think is nice because there's often a lot of confusion between the difference between crates and packages and workspaces. It can get a bit confusing. The use of installing binaries with cargo install and extending cargo with custom commands. So release profiles allow you to set a ton of compiler settings. So you've got the optimization level, the amount of debug info, debug assertions, overflow checks, link time optimizations, panic unwind or abort, which is what Richard touched on before in error handling when he's talking about whether or not you can get stack traces depending on whether or not you're actually unwinding when you panic as well. It's also allowing incremental compilation, the number of code gen units. So this is to do with parallelizing it for faster compilation, but potentially not getting the runtime performance that you might have done if you'd compiled it as a single block or just fewer blocks. And then also the runtime path, which is where you can pick up various binaries from to use. There are 4 built-in profiles in Cargo, which are dev, release, test, and bench, and you will have been using these without necessarily realizing exactly what they were a lot. When you've got profile dev, you've set the optimizations to 0, which should mean that you can debug stuff fine because it hasn't over-optimized your code a ton. You've got debug information to true. You can also have split debug info, but that's platform specific. Debug assertions true, overflow checks true, link time optimization is false, which is kind of interesting. Panic will always unwind, so that's why you get the nice stack trace. It does do incremental builds. It's got a ton of units. and there's no path set. You can override any of those as well. So switching on to release, so you can see the main differences are the debug assertions and overflow checks are set to false. Incremental build is set to false, which means you'll always get the full compilation, which is usually what you want when you're releasing it. Fewer codegen units, which should mean faster code, and more optimizations means you're giving the compiler more power to shuffle things about to its heart content, deeming it faster. So yeah, the overall is just that dev has fewer optimizations and more checks. Release has more optimizations but fewer checks. And test just inherits from dev, which makes sense because if you want to debug a test afterwards, then you want that information there. And bench inherits from release, which again makes sense because there's no point benchmarking a debug build. Don't do it, waste of time. And cargo is going to select the appropriate profile when you do cargo run or when you do cargo test and cargo bench. Those release profiles you can also create yourself in the cargo.toml. So here you can create one called release link time optimization, and then you can set link time optimization to true, inherit every other property from release, and then when you run it, you just do cargo build and set that profile flag to be release link time optimization. It will look in your cargo.toml, find that profile, and then it will use that to execute. So it's super easy to just modify these things in a really clear way. The optimization levels are probably the ones that play around with the most. Well, maybe not, but they're definitely an important one. So no optimizations means it will most closely match what you wrote. Basic optimizations, some optimizations, or all. You can also optimize for binary size, and you can also optimize for binary size, but turn off loop vectorization if for some reason you want to do that, to do with memory or some unique reason that you have. You can actually, I was reading about this, you can take it even further with profile guided optimizations, which you can do with other projects as well, but it's not something I've done before. I don't know if anyone else has, but it seems quite cool. So you basically, you can leverage LLVM tooling to gather the data from a typical runtime use. So you would execute your program with a certain input. Like say you've got a program that whips through does loads of image comparison data, or does a load of image analysis, or does video editing. You basically run it on a typical case and then gather the information. And then this tool will then generate a file that you can then pass to Cargo, and it will then pass that along to LLVM, and it will use that data to decide what optimizations are actually going to be effective for a standard use case. So rather than optimizing for a case that your software will never actually have, it will try and optimize for the most common use cases, which is quite cool. The quotes I got online was it could take like 15% out of your runtime, which is pretty huge in some cases. So yeah, play around with that if you've got slow code and a really easy to like generate use case where you can just run a standard example with a standard input and profile it. The next section is publishing crates. First thing to cover on that is doc. So your / comments that you write in your library on your public functions is going to become the documentation, which is really nice. It's then in place. You can edit it as you go. You can write your examples. You can write tests in your examples that are going to execute using doc tests, and it's just a really nice all round together system. So in this example, you've said, okay, I'm going to run on this config. This is the example from the earlier command line project. You can then say, okay, I'm going to set up my query, and then this is the example of how you would execute this method. So here I'm calling run using that config, and this is my little test. And then that way, when I come to generate documentation, or actually even before you generate documentation, even if you're just somewhere else in your program, so you've got your library that you're calling, if you've written some documentation, it will come up here. So you basically, if you've got like Rust Analyzer set up, if you set up your extensions, then you'll get it like a proper library rather than just one you've written yourself, but just from that / documentation, which is really nice. You can then view the doc that it would generate by doing cargo doc open, and you end up with something that looks like this. So the example that you'd written in the / will then become this example here. You can use markdown formatting for all of this. So you can make it as flashy as you like, all within those / comments. And the doc also gives you some additional information. So it will show you any re-exports that you did. So we came across this earlier in the crates chapter when we were talking about if your library relies on another library and you don't want them to have to reference that library every time they, for example, want to use an enum from it, you could re-export that enum. So here I'm re-exporting in my art crate, I'm re-exporting self-kind's primary color, it's the example they give. And then in the calling code, the primary color I can reference just from art. And if I've done that, it's not obvious necessarily to the user that that's what's happened. So in the doc, it will, I haven't put an example in, but it will generate a little list of this has happened so that you can see what crates are getting re-exported from it, which is quite nice. Publishing steps are super straightforward to follow, which is always nice. I mean, I guess it's a blessing and a curse because it also makes it very easy to publish not very useful crates, but it's still good to have. So you create your account, retrieve an API key, you log in, and from the command line so that you can store that API key on your machine. Do not share that API key with people because they will then have access to your crates. You add the metadata into your cargo.toml, like your license, your edition and stuff, and then you just do cargo publish. And then you're good to go. So if you've written anything that you think will be of use to anyone else, please don't be scared of the publishing process. It is that easy. The next section is cargo workspaces, which as your project starts to grow, you'll probably find that you maybe want to have one little library doing something, but then you, rather than just having it all within the same crate, you might want to pull it out. So you might have multiple applications using the same library. And for that, you might want to use a workspace, or even just for yourself to minimize having loads of binaries on your machine. If you're running out of C drive space, maybe a workspace would help you, because what a workspace means is that your dependencies will build to the same output folder, which means they're using the same version, they'll try and use the same minor version, and they'll just end up all in the same output folder, and they'll just be able to use the same binaries, the same built binaries. They'll also share the cargo lock file. The cargo lock file is where the actual version that you're using gets stored off. You don't hand edit that. It's just when you've done in your cargo.toml, this is the version I want to use of this library. Well, there's the major version, there's the minor version. You might have put a star and said, I don't mind which version as long as it's in the 2 release, for example. So put like 2.star or something. The cargo.lock, however, will actually say, okay, this is the one it was genuinely compiled with. This is what you used. And if you've got a shared common output directory, then you're going to share that cargo.lock file. It's worth mentioning as well, in the workspace level cargo.toml, you can set things like patch, replace, and profile. The profile is obviously relevant to what we mentioned earlier, but it's useful to have the shared ones in that cargo.toml. The reason why it references it is if you imagine all of those projects, the reason they're in a workspace is normally they're working together. And if they're working together, then you're probably going to want them in the same configuration at that point. And these are called the like cargo.toml files and things are called manifests, which is the word I probably should have known before this, but I just hadn't, which is called the toml file. So the workflow of dealing with workspaces would be just creating a directory and creating a cargo.toml file. You then specify what crates you're going to have inside it, or what packages you're going to have inside it. So you set up your members list, and then you create or move those actual member crates inside the workspace directory so that when you do cargo build, it will actually build them. And it's going to generate the output folder, which will be at the root of the workspace, and your cargo.lock file, which as I mentioned, has the all the versioning. And the resulting folder structure is going to look something like this. You've got your workspace level cargo lock file, you've got your workspace level cargo.toml, and then you've got your crate level cargo.toml, which is where you do, if you want to use a particular dependency, that's still going to be in the crate. That's not at the workspace level. But if you've got a particular release profile, that will be at the workspace level. And then you've got your source code and your output directory. And as mentioned, so by sharing a target output directory, that means the crates are going to avoid unnecessary rebuilding of dependencies that you've already built for another project. So there's a lot of common crates that you would be pulling in every time for every single project that you're building. But if they share an output folder, then it will just look for it and find it. if you want to reference one crate from another, they're not aware of each other by default. You still are going to use the same standard setting of the path in your dependencies, and this would be in your cargo.toml for your crate, not your top level cargo.toml, and you'll still just specify, okay, this is the dependency. I've got another crate in my workspace, and therefore I know it's one level up, and it's called other lib. When you run cargo build at the workspace level, that's going to build everything in the workspace. And within that, you might have multiple binaries, for example, and say I wanted to run, I mean, in this case, I've got a library and a binary, so it doesn't quite apply, but if I want to run a specific binary crate within my workspace, then I just do cargo run, which package, this package, my app, which in this case would be adder. And then you can have, this might reference, so the cargo.toml here might reference this library here, and it would do that in its own cargo.toml. It's worth reiterating as well that crates have to reference the dependencies from their own cargo.toml, as I mentioned. And if you want to add it to another one, you just add it to the dependency of that cargo.toml. It's just that once it's compiled, they then are sharing it. You don't have to compile it twice. So yeah, you add it to its own. So this is kind of true. All crates will use the same crate version from the workspace cargo lock. It is true, but it's not quite true. So it's worth bearing this in mind. It unifies on semantic versioning. So when you're doing your dependency, when you're listing your dependencies in your cargo.toml file for your project, you might be specifying the version in there. And if you specified version 2.5, and then in your other project you specified 1.4, it is going to pull both of those down because you said you specified two different versions. What can you do? If they're minor versions and you haven't made it clear that it's a specific minor version, then they will use the most recent 1.x version. But if there's a major version change, then it's not gonna combine them. So it's just worth bearing in mind. Pay attention to the ream of information coming down as it compiles, because that will show you what it's actually pulling down, what it's trying to compile. And if you see more than one version of a crate where you actually you don't really care about the version, then just make sure you haven't been too strict about your version for that particular crate.
So I think that kind of makes sense in terms of why you would want that to happen. But if you're going to go as far as to have separate ones for the major versions, I wonder what the motivation is for enforcing the same minor version.
Yeah, I feel like most of the time, yeah, minor versions shouldn't break. It just depends whether or not the crate owner has actually obeyed the the breaking changes policy of minor versions versus major versions.
That's true.
That's the thing. So even if you have two crates, one using the other one, but those two different crates having different versions of another dependencies, right? So if they share types of that dependency between each other, I wonder what that results in.
Yeah, exactly. That's one of the main use cases, is making sure you've got shared versions between things that are going to be referencing those same imports, and they want to have the same version. And this is just a way of kind of ensuring that. It's just worth mentioning, it doesn't actually ensure it if you've specified the version in your cargo.toml, which makes sense, because if you've said I want this version, it's not going to be like actually nah, because you've included this other project. It doesn't know how they all link together. It's not going to say, oh, but you're using this one, so I know that you need the same version as this one. It's not going to do that. So you would need to be a bit looser with your version specification in your cargo.toml, so that when you do when you update your dependencies, it will pull the latest version for both of them, rather than keeping you stuck on an old version.
Right, I see.
And I just wanted to make that note about profiles as well. So workspace profiles will be used instead of the inner profiles cargo.toml. So if you've created a workspace and then you're adding these profiles to your inner crate and you're wondering why they aren't applying, it's probably because you've got an outer workspace that is overriding those options. So there are two final bits in this section. They're so small that I fit them both on one slide. So cargo install binaries is just a really nice, neat way where people can share executables on crates.io. You can pull it down, build it, and just have it run really easily. It'll be added to the path if you've installed Rust the normal way, because they'll dump it in a location that's already in your path. Once you've created those binaries, you might also have ones that are that kind of playing with cargo. They kind of are similar to cargo commands, but they're not exactly existing ones. So if you have a particular cargo command that you want to do something like maybe there's a pre-step before you do a build or something, then you could say, for example, cargo extra build or something, and you could write a binary called cargo extra build, and then when you call this, it's called a cargo subcommand. When you do that, if it's in your path, this will work, which is quite nice. And when you do cargo list to show all the possible commands you could do with cargo, it will be one of them, which is quite convenient for your build system. If you've got little things you're running and you want them to just happen as part of cargo, then you can just set up your binary this way, which I thought was quite nice, quite neat. The install binaries especially, I think, it's just easy. It's just very easy to do. Rust makes things far too easy for us. Makes us lazy, but it's quite nice. So to summarize chapter 14, dang cargo, how you do so much. So it allows you to play around with profiles, modify things. You can even do profiling through that LLVM tool in order to pass that into cargo to get the optimal running for your program. Publishing is an absolute doddle. It's very, very easy. Workspaces work really well. They let your crates work together in terms of both your include paths, but mostly just sharing those dependencies, improving your build times by not having to rebuild the same dependency like 6 times for your different projects. And libraries are fun and all, but don't forget about the lowly binary, which there are plenty of great ones on crates.io. So if you've got any nice executables up on crates.io, have a peruse, see if there's any that take your fancy. And
I wonder if there's an instance of Doom on there.
And you can get cargo to do pretty much whatever you can write in an application, you can write as part of a cargo step by setting it up as a subcommand. Which is the end of chapter 14, and therefore the end of the section. It's quite a whistle-stop tour. They're two quite disparate chapters. They're quite separate to each other, but they are both quite good. You wouldn't want to do a whole session on just one of them, so I think it's quite nice to have them put together. Yeah.
Well done.
Yeah, thank you for that, Ciara.
You're welcome.
Thank you. We made it in time. How could you not mention a great presentation we had like a year ago about publishing a crate from CJ?
Oh, oh yeah. Was that in person or was that virtual? I wonder if there's a recording of that.
No, that was, I think, virtual.
It was virtual. Oh, it's probably a recording online. I'll find it and I'll post it on the Discord. But yeah, it can be done. It has been done. And yeah.
And we have traces.
Yeah. Were there any?
Sorry.
Were there any questions or anything in the chat? I should get something I should check.
Yeah, obviously, maybe a few more words about workspaces. I know there's a way how you can link the crates which are not in the somewhere nested in the directory tree. You can use crates which are in different places in your file system, and you can link them probably by putting into their toml file information about they are part of the workspace.
So as in you would have it not in the same workspace? Are you saying you'd have it just completely separate?
It is, but it's not subdirectory. It's separate from it.
Can you think what is the use case for something like that? Because like if you have a project like this, it makes it not portable between computers, right? Unless you have some bootstrapper that basically reproduces your file system structure, right?
So I thought maybe it might be something when you experiment with crates of the other people, and you wanna work with them in other place than your project. Maybe you wanna use this version in many of your projects, and it is probably impossible. You can link. I don't really know from experience, but possibly you can link the crate with only one workspace. So.
Mhm.
Yeah, I think it just gets tricky to manage as it grows. I think that there's 101 ways you could do it in terms of compiling the Rust code, but in terms of working with cargo, I think they've tried to make it as simple as possible. But but that does mean a bit less flexible. So you can do pretty much whatever you want. It's just, the road less traveled is also a harder path. So you can, if you want to set up symlinks, you could just have things compile. You could do things directly using the Rust compiler rather than leveraging cargo, and that would give you all of the flexibility you're doing, because behind the scenes, cargo's just setting up all of those linker paths for you. But you could do that yourself if you knew you had a particular workflow that wasn't working with cargo, then you could do it. But you just have to be a bit more careful, because it's not going to be able to keep everything in sync for you. So you're going to end up having to manage your own build system. Whereas the thing about cargo is it's providing a build system. It's not got all the bells and whistles of everything, but that's also what makes it so easy to use. It's incredibly useful, but it's not everything. It's not going to give you ultimate flexibility.
Cargo is like CMake, just a little bit more polished.
So other question, it's probably related, because I was asking, because maybe there's a playbook. We know this one when we have nested things. Eventually, maybe with the bigger projects, there's a pattern and the playbooks for other works. How to work with the workspaces, but it seems like a quite nice tool where you can operate with this with something which is quite not common dependency tree.
Yeah, exactly. It just gives you a little bit, it gives you a little nice kind of way of grouping them, but it doesn't really do a huge amount. It's not doing tons workspaces. It's just a nice addition on top of crates. To if you're working with more than one project that you're writing, then it gives you a way to group them together without having to do anything fancy. You just create a folder, add a cargo.toml, done. Put your crates in there. You've completed it.
That's also like a way of creating a monorepo, maybe, right, with the Rust project, right?
Yes, but I guess it's not one application, so I wouldn't. Each cargo, each crate is going to have its own Git repository inside it. So
would it, in fact?
Well, anytime you call cargo new, it sets up. I mean, you can delete the Git repository. You could measure it. You could do it at the workspace level. But when you publish, you can't publish a workspace. You can only publish a crate. So you would need a separate Git repo for each one of your crates, because otherwise it's not going to work in terms of.
So how would you normally work with the workspaces? Would you create a super repository and then Git submodules for each crate?
I would think so, something along those lines. Yeah, I think you'd have to do something like that, or you would have just, if you wanted to publish your workspace on Git somewhere other than just a local repo, and you didn't want to add all of the sub repos to just your Git ignore file, which is probably what I would do, then yeah, you'd need to do something like Git submodules to get it to manage them in sync. Mm-hmm. Yeah. I take your point though. Like, you kind of want them to be in sync if you're working with them together. So you Git submodules would probably be the way to go. So then you could update them all in parallel. If anyone tries it, if anyone ends up with a project big enough that it's worth having a workspace rather than just a crate, because it's with crates and packages, like with your package, you can have one binary crate and then many library crates, which means, and you can publish that package as one package onto crates.io. So you can get a huge amount of stuff in one in one cargo package. So you don't need to create workspaces most of the time. It's only if it's growing that little bit more and you want some separation, or say you're working on something else, you're like, actually, this would be really useful to work together with this. Or I think what I would probably use them for at this stage in my Rust usage, where I'm not building big projects, is probably just to share dependencies, because most of the time I don't care about the version of my dependency. It's very unlikely to break underneath me. So why not share the output folder? There's not really any downside. They don't depend on each other. You've got totally independent projects, just using it as a convenient way to share the output target directory. Yeah.
Do you have any experience with integration with other languages and with some wrappers of existing code and how to work with it? Maybe then could be worth to keep them outside.
Yeah, that's a good idea. So you've got your workspace that's just a way of grouping it. And you can, I guess that's true, you can just put whatever you want in there, because your workspace probably isn't under source control. It's just grouping some projects together. So yeah, that totally make sense.
Yeah.
I would still keep it at the source control. Just you control everything, right?
Yes, that's true.
You did mention, sorry. Yeah, I was to switch the topic, so go ahead.
Okay, so maybe the last one about this control about the workspaces, and could you build everything which is linked with workspace on the one time, or you need always to build it separately? Even from the root folder, you can access it by the name of the project, but could you build it like completely?
So when you do cargo build, even if you do it at the subdirectory level, if it's in a workspace, all the output will go into that target folder at the workspace level, which means it should only have to build once. If it's the same dependency, then that's kind of one of the main benefits of a workspace, is that, yeah, you don't have to recompile. Like the example they give in the book is, we got one crate that's pulled in, the one package that's pulled in the random crate, and then you've got another package that's also pulled that in. They're not in the same package themselves, but they're in the same workspace. And because they're in the same workspace, they share the output folder. And that means when one compiles the rand crate, goes into the target output folder. And then when the next one tries to, it says, oh, already compiled it, sorted. And then there's no, that's by virtue of the fact that they share the cargo lock file, because it's the cargo lock file that tells you whether or not you need to recompile it. That's why it's at that level. Cool. Over to Alex.
Yeah, if
Thanks, Alex.
there's no more questions, there's a tiny bit of housekeeping to sort out. But Christoph, you look keen to ask one more thing.
Yeah, I just want to mention one thing. So in the profiles, right, in the developer profile, you did mention that it might be weird that LTO is on the false side. But I think in the developer profile, so it just prepares you for working, like, you add something, you recompile, add recompile, and the LTO is just taking time, right? So it's just optimizing your time as a developer for it. And I think that's why also the incremental is set to true. So you have incremental recompilation, right? So you're already reusing what you can, just to get the compilation cycle as quick as possible. That would be my bet.
Yeah, that makes sense. That does make sense.
Yeah, and yet another thing, right? So with the easiness of publishing crates, I've seen somewhere people discussing that it's just too easy, in terms of many people just took over names of the crates and they just didn't publish anything, or just empty crate. And because of that, some sensible and nice names are already taken and cannot be used for nice projects, right? So because people are not nice, it might something like that might cause troubles.
Yeah, definitely. You can publish a crate without having any real skin in the game in terms of the Rust ecosystem. You can do, you can spend a day doing Rust and you can publish a crate. You could spend an hour doing Rust and also you can publish a crate. And people do it with it's not necessarily malicious, but it's just, why wouldn't you want to see your crate published on crates.io? It'd be great fun. But
It's
just,
like
you're stealing all the good names.
Yeah, and I think it is malicious in some cases. Just people, want to be dickheads, right, for others.
It's true, they do exist. People like that. I forget.
Yeah, it's quite likely that for non-malicious people, if you've read the chapter, you might be tempted to just go and make a crate just to prove that you can. So I wonder who the first person to write test crate 1 was. Test crate 1_copy. There's probably tons of those.
Yeah, I'm kind of surprised they put it in this early in the book. I would probably the odds of you writing something worth publishing before you've learned about smart pointers in Rust, I would say, is probably fairly low. So it sort of feels like you should maybe be like a footnote of if you've written something worth publishing, there are ways to do this, and then still have it completely accessible and available, but maybe just not so early on, because
or just the ability to remove it from crates.io. So I'm certainly guilty of making a crate before fully appreciating all of the language features of Rust. And now if somebody wants to make a project on crates.io called ftrack, you can't, because I'm hogging it with code I haven't touched for 6 months.
ftrack is useful. Don't do yourself down. That's a nice little project you did.
I tell you what, after the closures and iterators chapter, I am going to have to go back and refactor it, I think.
Now that you found out the for loops are passé.
Yeah, I wouldn't want to be unfashionable. Just while we're moving on, but we can continue the discussion afterwards. So next time we're planning to meet in 2 weeks' time, I believe, which will be, checking my calendar, the 3rd of February. We are aiming to just cover chapter 15 because smart pointers is quite a big, heavy topic. And I can't remember off the top of my head if we have any volunteers for anyone to lead smart pointers. Oh,
Christoph was a solid maybe, but I think we've turned that maybe into a yes.
I am tempted, really. I mean, if someone wants to take it, take it. If not, I will do my best, as best as I can.
I tell you what, if I'll get in touch, Christoph, if somebody's really keen to take over and lead us in the next 2 weeks for smart pointers, drop us a line in the Discord, just somewhere public, just say, hey, I'm interested. If not, I'm sure we'll find somebody to do it. It'll be a meaty chapter. It'll be a good one. I'm looking forward to reading it myself.
Yeah, me too. So say, Christoph, there's a good chance it's yours.
All right.
But yeah.
That's fine.
Right.
Yes. Oh, these are the dates I was just looking up. Yes. So as I said, smart pointers on the 3rd. On the 10th, we're planning to have what we call a speaker style meetup, which is sort of a presentation, or I think are we still fitting 2 in, Ciara, or are we doing 1 a session now?
Well, we have no speaker yet, so this is still a maybe, I would say, for the speaker session. I think my preference is probably shorter meetups, and we'll just try and get more of them in. So I think just 1 speaker would be good, because I think with everyone working from home, I think it's just tricky to, if everyone's gone somewhere, then it makes sense to have multiple speakers in a longer meetup. But for the virtual ones, I think keeping up that regularity but having a shorter sessions is preferable.
Sounds good.
But yeah, if anyone disagrees, then also I don't really mind.
Okay.
Happy to have more speakers.
We'll consider this a call for talks then. Anything C++ or Rust related. Again, drop us a line in the Discord group if you'd like to give a short presentation. And yeah, hopefully we'll have something excellent for everyone to watch on the 10th. And then 17th, we'll be covering the Fearless Concurrency chapter. And again, looking for volunteers on that as well.
Also going to be a very good chapter.
Oh yeah.
So-
And I think
Yes.
that is all of my housekeeping stuff.
I have to bounce. So yeah, see you all next time. You enjoyed that.
Thank you again,
See you next
Ciara.
time, Dave.
Bye bye, everyone.
These guys.
Bye bye.